Hello, everyone, and welcome to today's session, EMI Concepts and Board Shield Design Guidelines. My name is David Zimmett. I'm the president of Orion Technologies, Leadertech's representatives in Canada since 2016. I'd like to introduce you to today's presenter, Lee Branham. He holds a Bachelor of Science in Engineering Technology and Mechanical Design from the University of Central Florida and is certified Lean Six Sigma Green Belt. His specialization is beryllium copper gaskets and spring contacts, and he has been with Leadertech for 7 years. Hello, Lee. How are you?
I'm well. How are you?
Very well, thank you. So prior to beginning with Lee's presentation, we would like to ask you a couple of questions. At the end of Lee's presentation, we will have a Q&A and would love to hear from you. Lee will also show us a variety of samples he's come up with. You will also be able to download a couple of documents related to today's webinar topic. And when the webinar is over, we would truly appreciate your feedback about this and future webinars we are planning. Thanks. So that's about it, folks. So what we'll do now is we'll proceed with Lee's presentation, and then as indicated, we'll have the Q&A, the download of documents, and Lee providing us with showing us some samples. So Lee, we're going to let you go ahead and do your presentation.
Hello, everyone, and welcome to our webinar on EMI Concepts and Board Shield Design Guidelines. My name is Lee Branham. I'm an applications engineer at Leadertech, and I'm going to be guiding you through our discussion today. So to start with a little background on our company, Leadertech is located in Tampa, Florida. We've been in operation since 1984. We'd like to think of ourselves as a full-service EMI solutions manufacturer. We specialize in circuit board, enclosure, cable shielding solutions, and we also offer a full line of thermal products. You can see here that we really work with all aspects of industry, aerospace, military, commercial, and at this time we have 130 employees, and we do all of our manufacturing in-house at the Tampa facility. So Leadertech is a subsidiary of HEICO Corporation. HEICO is located in Hollywood, Florida. And what HEICO does is they are the largest provider of non-OEM replacement parts for the airline industry. They operate in two segments. They have a flight support group, and then they also have a electronic technologies group, which is what we're a part of. You can see they're a $2 billion+ company, and they acquired us in 1999. So the advantage of being owned by a larger parent corporation like this is that they're able to give us the capital support that we need to better support our customers. In this webinar, we're going to discuss the concept of EMI, as well as the guidelines for designing effective board level shields. So what is EMI? EMI stands for electromagnetic interference, and is essentially signals emitted either from or received by a device that disrupt its performance, similar to like a cell phone that could interfere with a speaker or TV. You don't generally see that happen in your day-to-day because those devices are shielded. If you look at the chart of the electromagnetic spectrum, we're looking at primarily the radio and microwave zone, just below the spectrum of infrared and visible light. The goal of EMI shielding is to mitigate this interference by creating a Faraday cage around the affected component. The total reduction in the signal is a combination of reflection loss within the Faraday cage and absorption loss actually within the material of the shield or cage itself. So what would be an example of a perfect shield? The ideal shield is a large, thick, hollow sphere of iron with gold plating for maximum conductivity and no seams, gaps, or openings. Obviously, this isn't manufacturable or feasible, because you wouldn't have any openings for power cords, cables, connections, anything like that. So we have to design our shields so that they still work in the real world, but they still provide the best levels of shielding effectiveness. In this slide, I've got a couple of basic shields. They're just one-piece boxes, as simple as it gets. And what I'm trying to show here is designing for apertures. When we talk about EMI shielding, we're trying to reduce the linear aperture. So if you look at the frequency wavelength chart in the center here, let's look at 5 gigahertz frequency and go over to the right to the 1/20th wavelength column. So you can see the maximum allowable opening is 3 millimeters. So for the shield on the left, we've got just a standard corner. So with the standard corner, it's cheap and easy to manufacture, but you're limited by the height of the shield. So if you had a 5 gigahertz frequency in this shield, the maximum that wall could be would be 3 millimeters. Otherwise, you're going to release signal and reduce your shielding effectiveness. So one design that we like to use is the interlocking corner. So you can see the shield on the right here. We've got an interlocking corner. So they're almost like teeth. So when you form the walls of the shield down, the teeth interlock and break up that linear aperture. So rather than having one long seam like you do over here, you have several smaller openings to give you better shielding effectiveness. Here I'm going to show you a few examples of different types of shielding products. You can see here on the circuit board, this is just a basic rectangular shield frame. It's part of a two-piece. This frame gets soldered onto the circuit board, and then you would have a removable cover that would snap on top of this. It's a fairly simple shape. It's just a basic rectangle, and if you design your circuit board correctly, you can use one of these, more standard type of products. These are a couple of different products that we make. This is an SMS shield, so these are standard off-the-shelf tooled up products. They come in a full catalog of sizes, so if you can design your circuit board to use a part like this, they're already made, they're on the shelf, they're the easiest type of product to use. This is a CBS shield, so if you look at the fence around the bottom section, you can see it looks like little fingers. So those are straight pieces of fence that we can form to different lengths and widths, and we have different options for heights. So it's kind of a modular design. So if you don't have something that's made for the ready-made off-the-shelf parts, we can design a shield like this that is kind of a modular type of design. The slot lock shield is a fully customizable type of shield. So when you can't make a standard product fit on your board, we can make this type of customizable shield that will fit to what you've already designed your board to be. And then this shield is an example of a fully customized product. Something like this is when EMI is an afterthought. And obviously something like this would be by far the most expensive type of shield. When we're designing an EMI shield, the first aspect that you look at is what type of material you're going to make the shield out of. So you have to ask yourself, how is the shield going to be used? Will it be in a corrosive environment outside, in a vehicle maybe, or is it going to be indoors in a protected environment? So we have multiple options of material. So the alloy 770 is a copper nickel zinc alloy. It's what we use for corrosion resistant designs. It's non-magnetic and it doesn't require any plating. It's also what we use when we need to design a part that is welded from multiple pieces that have to be put together, so it welds very well. It also has excellent solderability. The next material is pre-tin plated steel. So pre-tin plated steel is our standard type of material. It's cheap, it's easy to manufacture, it has excellent solderability. The trade-off is it doesn't have good corrosion resistance. So if you were going to use this shield where it would be subjected to moisture, uh, the the metal has been plated from the mill, from the material manufacturer. So when you cut that metal to make a shape, uh, you're exposing the bare edges of the steel, and they can be subject to corrosion. That being said, we make the vast majority of our products are made with this pre-tin plated steel, and it works for most applications. Um, Another type of material is a phosphor bronze. This is a good material. It doesn't require any type of heat treating, but it does have moderate spring properties. So we've used this before. Say you had a shield that has a connector going through it, and you would put a type of a light spring finger to make contact on that connector and give you good grounding. That's something where phos bronze would come into play. The phosphorons does come pre-tin plated if you need it, but generally we see those are being post-plated after processing. Um, we do have the option to make shields out of pure copper. It is expensive, but copper does provide the highest conductivity, and technically it does give the best shielding, especially at higher frequencies. Um, you don't generally see customers needing to make a shield out of copper. It's not usually necessary. Generally, copper is reserved for battery contacts, connectors, things like that. And the last material on here is high mu 80. So when we were talking about the electromagnetic spectrum earlier, below what we saw for radio frequencies are magnetic frequencies, so in the hertz and kilohertz range. So earlier I had also mentioned about the EMI signal being absorbed into the material itself. So high mu 80 is a high permeability, so it essentially soaks up magnetic frequencies almost like a sponge. So that's a special type of material that we use for only low frequency applications. So in addition to trying to design a shield for good shielding purposes, you're also trying to make these parts easy to install. So there's a few aspects of the design that you have to look at when you're considering how you're going to install the parts on your circuit board. So the first we look at is what type of edge, whether you're going to have pins, solid straight edge, or castellations. So pins are sometimes used when you're doing wave solder, where they protrude through the circuit board and then it passes through a wave of molten solder, and then the pins are soldered underneath the board. Um, or pins are also good if you have a very complex shield. They can be used to hold it in place onto the circuit board trace. Solid edge is when you're doing SMT, where generally the shield is going to be automatically picked up and placed onto a circuit board. And then castellations are an interesting option where it breaks up that continuous solder trace and helps get good airflow and more even heating to get a better solder joint. Um, when you're looking at doing a shield, you have to decide whether you're going to do a one piece or a two piece. One piece is just a box that is directly soldered to the circuit board, and then it's not coming off. The other option is to do a two-piece frame and cover. So the frame is soldered down onto the circuit board, and then we design a removable cover. So this allows you to access components underneath while still getting great shielding effectiveness. When you're designing a shield for installation, one of the largest challenges we face is coplanarity. So These circuit board shields are generally installed in the same production line or manufacturing process that you would install a microchip. So it's a challenge to fit sheet metal parts into that same process. No matter what you do, those sheet metal parts are never going to be as precise as a mass-produced microchip. So we have to work with the customers to design for the coplanarity, the flatness. So you can see this shield. This is an example here of a shield where coplanarity is a challenge. So you're making this part out of welded pieces of sheet metal, and it's not going to always be very flat. So you can see this shield has multiple pins all the way around the frame, so that will help hold that shield in place on the circuit board. But it may not be very flat. So generally we see solder thicknesses between 3 to 4 thousandths, and that's not going to work with a very complex shield. So one thing we always try to get our customers to work with and use are fixtures. So these are a couple of examples of board level shield fixtures. So the shield would be placed onto the circuit board along the trace pattern, and then these fixtures are bolted down to hold them flat against the circuit board as they run through the reflow process, and that helps to ensure that you get a good solder joint. These are also useful if you're soldering on both sides, so the shield would run through one cycle and then the board can be flipped over, and because of the fixture, the shield will stay in place as it's run through another round of reflow for components on the other side of the board. Throughout the presentation here, we've been talking a lot about traces and designing shields to fit on the circuit board trace. And proper trace design is one of the biggest key components for being successful with installing your circuit board shield. Over on the left here, you can see this is a circuit board trace, and then this frame is installed on the trace. When we talk about the trace, we want it to be a minimum of 3.5 times the material thickness. So this diagram here, this represents the straight edge of material of a circuit board shield, and the circuit and the solder joint, the trace pattern would be here, and we need that trace pattern to be an absolute minimum of 3.5 times what the material thickness is. So if you have a 10 thousandths thick metal, you need a trace thickness width of 3.5 times that, for 35 thousandths. And what that does is it ensures a good solder joint. The solder wicks up the side of the shield, and it gives you a good solid joint. Again, 3.5 times is the minimum. We always recommend more if you have the room on your layout, but that's definitely what we recommend. So the last aspect of the shield design is actually getting the finished product to you intact. The parts that we make are small, and they're made out of thin gauge sheet metal, so they tend to be kind of delicate or fragile. So we have some standard packaging options, but depending on your application, we have a couple of special packaging options. So the first one on the left here is tape and reel. So you can see that these are shield frames that are installed in a plastic tape in pockets, and these are designed to run through an SMT line. Uh, so any type of shield that's generally going high volume, we're going to put it in this type of packaging so that they work on the SMT line. If a shield is very complex or larger and it won't fit in tape and reel, we like to put them in a plastic tray. So you can see on the right that this is a thermoformed plastic tray. And what that does is it helps protect the part in shipping. Again, the shields are generally somewhat fragile or delicate. So we have to make sure that they make it to you intact. This concludes our presentation today. I hope it was enjoyable and that you were able to pick up some good information on electromagnetic interference and how to design products for easier installation. On the screen here are the Leadertech contacts. So we have Tracy Coons is our president. Todd Kerrigan is our regional sales manager. I'm Lee Branham, the applications engineer. Lily Higa is our account representative. And then I've included David Zimmett of Orion Technologies, and he is our manufacturer's representative in Canada. Thank you for your time.
So the first document is basically a drawing of a standard one-piece shield. Let me share that with you. The following document is basically a Slot Lock Pro assembly drawing. Any comments, Lee, with regards to?
So these drawings, we like to call them like a menu drawing. They show a variety of options: vent holes, pin sizes, edge designs, and you don't have to exactly adhere to everything on this drawing, but this gives an array of options that you can choose when you're designing your shield.
Okay. And then the last document is a brochure of board level shields, the different variety or flavors that Lee alluded to in the presentation, including surface mount shields.
Yeah, it shows a little bit of everything in there.
Right. So Lee, maybe you want to share with us a couple of samples you've picked.
Yeah. So to go along with what we talked about in the presentation, I have a couple samples here. So we talked about how the shields are formed. This is an example of a flat blank with the interlocking corners we talked about. So this is how the shields start, and then we form them, the walls down to make the box. So this is a formed slot lock standard shield. You can see it has the interlocking corners there, and this is a pretty basic design. So when we were talking, when you get into more complicated shapes, we were talking about the Slot Lock Pro. So that's made from a straight piece of fence that's welded. So here's an example of one of those. So I don't know if I can see, you can see the welded corner here. So this is made from a straight piece of fence, and you see it's a little bit of a complex shape. So that's something for a board where you need more than a rectangle. The Pro allows you to do multi-cavity. So here's an example of a very low profile multi-cavity. So those are small fences that are welded in, and then there would be a cover that would snap down on top of this shield. So we can go very, very low profile, especially on the Slot Lock Pro shields. When we were talking about packaging, we discussed the tape and reel. So here's an example of our standard off-the-shelf SMS products. So these come packaged in tape and reel, and I cut a small section off, but this would come on a large a reel, and that gets installed onto the SMT machine. It pulls back the cover tape, and then it picks and places these parts onto the board. And I have an example of a plastic tray. So this is an example of one of our thermoform custom plastic trays. You can see it's kind of an odd pocket shape, so the shield gets placed into these pockets, and then they usually stack so they can keep the shield protected when we ship them to you.
Great, thank you. By the way, folks, Leadertech is very good at providing some lab kits. I just have an example of one kit here. This one is called the Kit 16, and it has a variety of shields, for you to be able to play around with, strips as well. Leadertech also has a similar kit strictly for surface mount, one-piece or two-piece surface mount shield. So please, most of the all of the Orion offices have these kits in stock. And if you're not in Canada, then please contact Leadertech. They'll be very happy to provide you with one of these sample kits.
Yeah, they're a good ideas kit for you to see all the different designs, touch them, feel them, see how they fit on your board. You can kind of feel how the parts are made.
Okay, great. So, folks, we'd like to proceed with the Q&A. Either write your question if you would like to appear on screen, or you would like us to hear your fantastic voice. We'll turn you on. So I actually had a couple of questions that I know that there is concern sometimes with regards to maintaining a solid base for that shield on the board, and obviously you have solutions called the tech clips. So what is the recommendation with regards to using tech clips? General rule in terms of how big that shield can be to use those tech clips, and when is it appropriate to use those tech clips?
So the tech clips, we were talking about coplanarity earlier with complicated shields. So the tech clips give you a good option. Instead of using a frame like this, you can place tech clips around this trace, and then you make a solid cover that would snap into the tech clips. So the tech clips are very small and they come on tape and reel. So they work very well with the pick and place. They're similar in size to the other components, the electronic components being placed on the board. So because they're small, you can place them easily and you don't have to worry about a frame, a large frame not sitting flat. You don't have to worry about rework. You'll have gaps in between where the tech clips are placed. So generally they're for a little bit lower frequency. If you were at 20 gigahertz, you wouldn't want to use them. But if you have a larger, more complex shield, it is a good option.
Okay. And what about thicknesses? You kind of talked about thicknesses of shields and so on. What are some of the standard thicknesses?
So our standard material thickness is 15 thousandths. I don't know the millimeter off the top of my head, but 15 thousandths thick. And we have materials all the way down to 4 thousandths thick. But we always start with 15. And then generally, if a shield is a little bit smaller, we'll make it out of thinner metal to make it easier to form. It's kind of hard to put a tight bend in very thick metal. We go up to 20 thousandths thick in pre-tin steel and the alloy 770. And we generally don't use that unless you have like a very ruggedized application where you need like vibration resistance, or if you're installing standoffs or inserts, the thicker material works better for that.
Okay, great, thank you. So we do have a couple of questions. The first question for you, Lee, is how to decide shield wall thickness? What are the parameters to decide what should be that thickness?
Yeah, that's kind of what we were talking about too. So one thing to take into account is how large you can make your trace pattern. So if you can only make it 35 thousandths of an inch, if you only have that much room, then you need to use a little bit thinner metal to keep the 3.5 material thickness minimum that we recommend. There also comes into terms of how small the shield is. So if it's a smaller shield, we'll make that determination to use thinner metal. There's not an exact rule of thumb. Usually when you end up seeing a design from experience, you know what material will work best. But then we make a 3D model so you can see how that part will fit into your assembly.
Gotcha. Okay, the next question is, how do you manage heat when using shields? Can shield be used with a heatsink?
So our shields, they can be used with a heat sink. We offer a full line of thermal products that can be installed in conjunction with the shield to transfer energy from a chip to the shield, or you could even place it on the outside to transfer from the shield to a heat sink that's above the cover.
Okay, and I know that Leadertech also manufactures some microwave absorption materials, and again, there you could use this material in conjunction with the shields to achieve whatever performances you're looking for.
Yeah, the absorber is generally used in conjunction with the shield when you need just a little bit more attenuation than the shield is providing. So we will select an absorber based on the frequency that you're experiencing and install that to the underside of the cover, and it soaks up the signal and gives you better performance.
Okay. Here's a pretty common question that people ask me. What percentage of your shields, the shields that you manufacture, are custom? Because custom for a lot of people means expensive dollars. So maybe you want to just run through that. How many designs are presented to you that are custom, and does that make it a very expensive proposition?
So we have all of these standard products in our catalog. Um, but again, a lot of times it's not going to work. So anything that is a slot lock is considered a custom part. And that's just because everyone's application is different. So custom parts are standard for us. The vast majority of parts that I work on are custom products. So it's not scary business to do a custom. That's all I work on every day, and the vast majority of my customers deal with a custom product. But if you have a standard product where you have to add a hole or a notch or something that's just not out of the catalog, anything that requires a drawing technically becomes a custom. But we've standardized and streamlined the process to do customs. Again, we make a full 3D model and a drawing, and we have our customers review and approve them before we cut any metal, so you don't have to waste time and money on prototyping. We do it all with the 3D model. So that's our recommended process.
And as a follow-up question, because I guess you've explained that a custom for you is kind of a standard, but what are the expectations in terms of turnaround time? For you to provide a final drawing of that custom shield for the customer's approval, and an approximate lead time to turn around, either a pre-production or production lot of these custom shields.
Okay, so let's talk prototype quantities. Anything less than 100 pieces, right? So again, it's dependent on the complexity of the shield, but something like this, while it may look custom, is for us is fairly simple. So it would only, from the time you place a purchase order, it would only take 2-3 days at the most to get you a drawing. Usually we can turn around quicker than that. And then a lead time is typically 2 to 3 weeks after you approve the drawing. So that's it. It doesn't take very long. Again, we've gotten very good at the custom process. So I know sometimes it's 6-8 weeks to get custom products from other manufacturers, but 2 to 3 weeks is a pretty good average time for a relatively simple custom part.
Okay, thank you. Are you able to supply shielding magnets in 0.5 millimeter mu metal material, or what would be your alternative?
So we use high mu 80. I guess mu metal is a trademarked material. So our alloy is called high mu 80, and it's essentially the same type of thing. It's a high permeability material. We have it in stock in 6,000 thick and 14,000 thick. So those are the standards that we carry, but it's fairly easy to get different thicknesses of material. Mu metal is expensive, so again, if you need to use it, we need to make sure that you have the right application to use it. But it cuts, it forms, it welds just like any of our other materials, so it's not really an issue to use it.
Okay. Another question that comes up is at what stage, when a customer is involved in higher volume applications, does it make sense to develop a progressive die? And what is the point of a return on investment to invest in a progressive die for higher volume manufacturing?
So for a standard slot lock shield, something like this, just a rectangle, anywhere in the realm of 8 to 10,000 pieces is about your break-even point on a tool. And again, that depends on the size and the complexity. But for a basic shield, if you're going to use more than 10,000 a year, usually it makes sense to invest in a progressive die, and you turn a $3 part into a 50-cent part, for example. But it's that's usually 10,000 pieces is where you see the payoff. That's if you're asking 10,000 pieces, I will quote tooling options. So you can order prototypes while we're starting, and then we can do tooling at the same time.
Right. And obviously, if a customer can accommodate one of your standard developed one-piece or two-piece surface mount shields, where you have absorbed already the cost of that progressive die, and then that's going to be, again, a relatively not costly solution.
Yeah, the SMFs are the most cost-effective parts. They are the least expensive parts we offer. They're on the shelf, so generally it's next day when we can ship them to you.
Okay, gotcha. All right. Any other questions, folks, for Lee? Okay. Well, Lee, I really thank you for your time. Great presentation. And thank you, Leadertech, for participating in our webinar series. And of course, thank you to all the attendees. I remind you that we would truly appreciate your feedback with regard to today's webinar. So you have, I think, 5 questions that we would like to get you to respond to. We will have more presentations from Leadertech. The next one most likely will cover, I believe, enclosure shielding. So please take your time to answer that webinar survey, and thank you so much for your precious time today. Have a great day.
Thank you.